I am not throwing away my shot. I am not throwing away my shot. Hey, yo, I'm just like my country. I'm young, scrappy, and hungry, and I'm not throwing away my shot.
So the first thing before I do anything for this lab, I actually need to turn on my spectrophotometer. So this is my spectrophotometer right here, and I'm gonna turn it on because I've got to give it about 15 minutes to warm up. Okay. And once I figure out what wavelength I want to set my spectrophotometer to, I can do that at any point. Okay, and so this is where I manipulate my wavelength to set it to the wavelength that I want to. And this is where I'm going to put my cuvettes. That's the sample container. Okay, so let's let this warm up. Let's make my solutions. So the first thing I'm going to do, I'm going to zero my scale, and I need to find the mass of my brass shell casing. So this is my shell casing here. Okay, and that is the mass of my shell casing. So the goal of this lab is for me to determine how much copper, the mass of copper that's in this brass shell casing. And the way that I'm going to do it is I'm going to take this shell casing and I'm going to dissolve it in nitric acid. And you'll see that in just 1 second. All of the copper in this brass shell casing will then be in solution. And when copper ions are in solution, they are colorful. Okay, they're a blue color. And I'm going to use spectrophotometry in order to determine the concentration of copper ions based on the fact that they are blue. But in order to do that, I need to create a Beer's law curve. To create a Beer's law curve, remember, I have to plot absorbance versus concentration. And so I gave you guys the task of determining how to create 5 different concentrated solutions. 0.4 molar, 0.2 molar, 0.1, 0.05, and 0.025 molar. I'll then put those into my spectrophotometer in order to determine the absorbance of each of those. Once I have those absorbances, then I can plot a Beer's law curve, or you can plot a Beer's law curve, and then we can actually determine the amount of copper that's in this brass shell casing. But I first have to create my plot. So what I'm going to do right now, I have 0.4 molar copper nitrate. Okay? And so what I'm going to do is I'm going to create those 5 different solutions that I asked you to create. The first one, okay, I obviously am just going to be using, because I want to find a volume of 8 mils, I'm going to just be using 8 mils of this copper nitrate solution because I want just 0.4 molar. Okay, so I'm going to show you how to use this tool. This is a volumetric pipette, and so what's really cool about it is you can actually, when you scroll up, it'll pull up the substance, and then you can actually push it out in order to expel the contents of the pipette. So let me show you how that works. All right, so I'm first gonna add 8 mils of my stock solution to this cuvette, right? Because I want a 0.4 molar copper nitrate solution. So let me show you me doing that. So I'm gonna scroll up, okay, and you can see it coming into the volumetric pipette, okay? Now I've added more than 8 mils, so let me show you how to expel it. So there are large markings, right? That shows a 2 there. But what I'm actually looking at is the little marking right there. Okay, it's really hard to see, unfortunately. Okay, but that says 8 mils right there. Okay, so I'm gonna release by simply pushing on this button right here. Until I get 8 mils, and you can see the 8 mils right there. Okay, so I'm gonna add that to my cuvette, my first cuvette, and that will be my stock solution. A couple of important things to note about your cuvette. Make sure that you're holding it on the top, don't put any fingerprints down below, because what's gonna happen with the spectrophotometer, it's going to shoot visible electromagnetic radiation through this cuvette. And so if you allow your fingerprints to get on the cuvette, your fingerprints themselves will absorb light, causing the absorbance, which is what we're measuring, right? The amount of light that is absorbed by the substance to be higher than it really should be. So make sure you're only touching from the top, okay? And leave the rest of the cuvette alone. Don't touch it.
I'ma get a scholarship to King's College. I probably shouldn't brag, but dag, I'm amazed and astonished. The problem is I got a lot of brains but no polish. I gotta holler just to be heard with every word. I drop knowledge. I'm a diamond in the rough, a shining piece of coal.
So that was the first solution. The second solution, I want 0.2 molar. And so what I'm gonna do is as you guys noted, I need 4 mils of that. So I'm gonna scroll, actually release, okay, and then I'm gonna scroll up to get 4 mils in my volumetric pipette. So let me show you that volume really quickly. Get it as exact as possible. Okay. Okay, so it's hard to see, but that's 4 mils right there. Okay, so I'm going to take that and I'm going to put it into my graduated cylinder because I want a final volume of 8 mils. So what I'm going to do, I added 4 mils of my stock solution into my graduated cylinder. Now I'm going to take distilled water in a pipette, a regular disposable pipette, and I'm going to add enough water to get a final volume of 8 mils. And obviously I should be doing this flat on the table, and I'm going to check it in a sec flat on the table, but I just wanted you guys to be able to see. So I'm going to bend down. I've got 8 mils exactly. Now I can pour that into another cuvette, making sure that I'm only touching the top of it, not the sides where the electromagnetic radiation is going to go through. Okay, so that's my next solution. Okay, for the next solution, okay, I need 2 mils of my concentrated solution, as you guys calculated. So I'm going to scroll up and get 2 mils. Okay, so you can see 2 mils right there. Unfortunately, it's not super clear, but I'm going to expel that. I'm going to rinse out my graduated cylinder. Okay, and then I'm going to pour that in. So I've got 2 mils of concentrated solution, which means I need to add approximately 6 mils of water, but I just want to get a final volume of 8 mils. Okay, so now I have 8 mils of this solution. Okay, so I'm going to pour that into another cuvette. So now I've got 3 different concentrations of my copper nitrate solution that I'm going to use for my Beer's Law curve. Okay, and I need to get 2 more. So for the next one, I need to add 1 mil of my concentrated solution. So I'm gonna, again, scroll up. It's gonna be just a tiny volume. Okay. So I've got 1 mil right there. It looks like it says, so the 9 is at the same place that the 1 is. Trust me on that one. Okay, so I'm gonna add that to my cleaned out graduated cylinder. And then I'm going to add enough water to get a final volume of 8 mils. Okay. And I've got just 1 more to do. Okay. All right. And then I need to get my 0.025 molar. And so the way I'm going to do that is I'm going to collect 0.5 mils, so a half mil of my stock solution. Okay. Put that into my graduated cylinder. Then I'm going to fill it up the rest of the way with water. And that is my most dilute solution. All right, in order to use the spectrophotometer, in order to determine the absorbance for all 5 of these solutions, what I'm going to first have to do is, just like with the electric scale, and I zero the scale, I'm going to have to zero my spectrophotometer. Okay. Before I do that, I wanted to quickly show you all of my solutions. So you can see this is the most dilute solution that I just made. This is my 0.4 molar solution. Okay, so you can see how they're increasing in concentration. And I'm going to measure their absorbances, and we're going to measure them, record them, and use the Beer's Law curve for that. So notice my spectrophotometer is ready to go. I now need to set my wavelength before I can do anything else. So if you notice here, we had noted that the best wavelength, remember, we want maximum absorbance, but we want the absorbance to be under 1. So I'm going to set my wavelength to 680. Okay, and then after I set it, I don't need to deal with anything else with respect to wavelength. That tells my spectrophotometer, please shoot out electromagnetic radiation that has a wavelength of 680. So I'm not going to change that at all. Okay. Now what I'm going to do is I am going to zero my spectrophotometer. So I get my water sample here. I'm going to wipe it with a Kim wipe to get rid of any fingerprints. Now the one thing for you to note, as long as your solution is high enough in order for the electromagnetic radiation to pass through, it doesn't actually matter what volume you put into your cuvette. So if I hadn't put all of the 8 mils of solution into the cuvettes, that would have been fine. The one thing you really have to be careful about with your spectrophotometer is to make sure that you don't fill it up all the way up to the top, because this is exactly 10 mils, that it spills over and destroys the spectrophotometer. Okay, so I'm going to put my sample in. Give it a good little push. Okay, and notice it is not 0 right now, so I'm going to hit 0. So it's blinking right now. Okay, and now I'm ready to go. Notice it tells you the transmittance. That's the amount of light that the sample is letting through, which makes sense. It should be 100% since I have pure water, distilled water there. And the absorbance should be 0 because none of the electromagnetic radiation should be absorbed at this point. Okay. Now what we expect, and one way for us to know if our readings are correct or if they're incorrect, is as your concentration of your solution increases, the absorbance should increase as well, because the darker the color is, the more light is going to be absorbed. So let's see if that happens. So I'm now going to go through. I'm going to start with my most concentrated solution. So I'm going to start with my 0.4 molar copper nitrate solution. Okay, and you're going to see the absorbances and you're going to record them. Okay, so that is the first absorbance. Okay, so record it. So that's for the 0.4 molar. Okay, for the 0.2 molar. That's the absorbance, which is in line with what we would expect because your absorbance is decreasing. Okay, for the 0.1 molar. And remember, between each one, you need to be wiping off your cuvette with your Kim wipe, which I'm doing. Okay. So that is your next absorbance. So that was for 0.1, for 0.5 molar, for 0.05 molar, sorry. I'm gonna wipe off my cuvette with the Kim wipe. Put it in the machine. Okay, 0.317. And for my last absorbance, that's my absorbance. So if we had been in the lab, the very first thing we would have done before we created our solutions and put them in the spectrophotometer is we would have put our shell casing into nitric acid. Okay? And so that would have been running this entire time. Now, obviously, since none of you guys are here, what I'm gonna do is I'm gonna cheat a little bit.
And I am not throwing away my shot. I am not throwing away my shot. And yo, I'm just like my country. I'm young, scrappy, and hungry, and I'm not throwing away my shot. I am not throwing away my shot. I am not throwing away my shot. And yo, I'm just like my country. I'm young, scrappy, and hungry, and I'm not throwing away my shot. It's time to take a shot.
I dream of life without a monarchy. The unrest in France will lead to anarchy. Anarchy, how you say? Or anarchy. When I fight, I make the other side panicky with my
Yo, I'm a tailor's apprentice, and I got y'all knuckleheads and local parentis. I'm joining a rebellion, cause I know it's my chance to socially advance. Instead of sewing some pants, I'm gon' take a shot.
But we'll never be truly free until those in bondage have the same rights as you and me.
So what I would have done is I would have dissolved the copper shell casing in the nitric acid. When it was done, I would have diluted that solution and given it to each of the students. They would have then put it into a cuvette, and that it would be a blue solution. That blue solution we would then put into the spectrophotometer to determine its absorbance. Okay, and so I'm going to give you that value right now. So the purpose of the lab is to determine the amount of copper, the percent of copper that's in that shell casing. So the first step we need to do is take the concentrations of the dilutions you created, and we need to plot that versus the absorbance. You're going to create a scatter plot and you will find a best fit line. So that's your first step. So if you need help with using Excel to do that, please make sure to watch the video that I included on Schoology. Once you have your best fit line, remember that is your Beer's law curve. What you can do then is take the absorbance of the brass shell casing solution, and you can plug that into your Beer's law equation in order to determine the concentration of copper that is in that solution. Using that information then, you can actually calculate the mass of copper that was dissolved into the brass solution, and from that then you can determine the mass percent of copper that's in the brass sample. All right, so you've got all of the tools at your disposal. Now it's time for you guys to analyze it. The last thing is for you guys to actually look up online the percent mass of copper that's in brass shell casings. Now, obviously, that'll vary based on the shell casing, so it's fine if you guys find different values. That will be your actual mass percent. Then whatever you got experimentally, that'll be your experimental, and then you can find your percent error.